All righty, folks. How y'all doing today? All right, luckily we got a little bit shorter of a video this time, so sweet. All right, we're getting back to something that actually back to being a little bit of a review. So today's going to cover complex numbers. Now, we don't have written out notes for complex numbers, so you guys are going to have to take regular notes in general. So you're not going to be following per se right out of an outline. So complex numbers. Well, first of all, we've dealt with real numbers. And real numbers are anything like 3, 7.1, 5/3, pi, square root of 2, all just pretty much every single number under the sun. There we are. Now, real numbers, we've also graphed them when we paired them up. We've graphed them together. And they've been really nothing more than some x and y. So if we take some real numbers and we write them as a coordinate, we were able to actually graph them. So like, for instance, the point 3, 1. We'd go to the 3 on the x-axis. We'd go to 1 on the y-axis, and friends, we'd have ourselves a point 3, 1. So those are our real numbers. And then back in integrated 2, we learned about our imaginary numbers. And really, imaginary numbers are anything that have some sort of I after it, because we said that essentially back in integrated 2 that I was the square root of -1. So pretty much you could take any of our real numbers and add an I at the end of it, and you would have an imaginary number. So pi I, that's a fun one. Root I root 2. We don't want to forget the number e. So we should probably have that one in there as well. Get all our constants in there. E, I. Anything that has a real number after, or any real number that has an I after, well, it just became an imaginary number. Well, complex numbers, which is what we're talking about today, is that idea of taking those and putting them together. So imaginary numbers are anything that has the form A, the real number, plus bi, the complex number. And just like we're able to graph a real number, we can also graph some sort of complex number. And ultimately, it's the same thing. So it would look like this. Let's draw one of these. Whoop. We don't have x and y. Instead, what we have, the a-axis, so the real number axis, and the b-axis, or some people call it the bi-axis. It doesn't matter if you put the I there or not. And that would be the imaginary axes. And say I wanted to graph a complex number, well, that would be the point right here. So this point I would have graphed in would have been the point 3, because that's the real number, plus 1i. So the real number always comes first in a complex number because it's like the x-axis. So imaginary number always comes last because it's the complex. So we have this idea of our complex plane. And this imaginary number is always based off the idea that I equals the square root of -1. So that's a little review there. And we're going to be playing with imaginary numbers today. But before we can do that, we need to make sure we have a little bit better idea of i's. Now, back in integrated 2, we talked about 4 of these. So anything to the 0 power is 1. We said I to the first is I. We said I to the second is -1. And then we talked briefly about it, but we didn't get much into it. But we said pretty much this last one is the third one, which is negative I. And by the way, if I wanted to go one step further and say I to the fourth, we called that 1. And we had a kind of a cute little way to remember the order of all these I values. We said to go ahead and always cheer for ourselves, because we always want to be our biggest cheerleader in math. And we said we should always say I won, I won, referring to the idea that I is always the first, I is always the first and the third, and 1 is always the second and the fourth. So we can remember these ideas. And we said it doesn't really matter what happens in the middle. So you can feel negative in the middle as long as you always remember that you want to feel good about yourself starting and always feel good when you end. So positive at the ends, negative in the middle. So we talked briefly about this idea, this pattern here of these 4 I's. And then the other thing that we got into a little bit, we didn't play much with, but we said, hey, these I's kind of go on forever. So I to the fourth, well, that turned out that was also I to the 0, or was equal to it, and that equaled 1. We said I to the fifth was like I to the first, because this idea that these 4 I values, no matter what the remainder is, they repeat themselves over and over again. So we talked about this in integrated 2, and we talked about it again in integrated 3. So we're going to start off, and we're going to kind of pick up here a little bit. We're just going to, all we're going to do today is do some simplifying. We said, by the way, that this kind of goes on forever, right? And we all, just for the fun of it, let's make sure we put this one up here as well. We also said, hey, by the way, this periodic pattern, this repeating pattern, also applied to if we had negative exponents too. Notice all these exponents are 4 away. We said that's why we only need to remember I to the 0 to I to the 3. And if we don't necessarily remember doing all this in general, not the biggest deal in the world. We're just going to kind of go through this idea from here. And as long as you remember the pattern of the red, you'll be in great shape. So we don't need to necessarily remember every single exponent. All we really need to do is remember this middle one. So what we're going to do here, friends, is I'm going to throw out a few problems for y'all. Today is pretty much just a review day. So I'm going to throw out some random problems for you all to solve. I'm going to have you pause the video, solve it, and then I will go ahead and walk you through them. So say I give you the first one. So let's make this a square root of -64 plus the square root of -25 minus the square root of -81. Oh, let's make this one I to the 31st. I want to know what that is. And last thing, let's do this as well. How about I to the 15th minus I to the 27th plus I to the 71st minus I to the 22nd, something like that. All right. So pause video. Let's see what you guys can do with these, and then we'll go from there. All right, here we go. So we said -64. We always said, let's treat this as -1 times the square root of 64. Break these up. So square root of 64 is 8. The negative makes it 8. I. So 8I plus 5I. Square root of 25 is 5. Square root of 81 is 9. So that'd be 9I. Combine them all, we get 13. Again, with the exponents, we said, hey, divide them by 4. And remember, we divide them by 4 because we have 4 numbers in our pattern. So whatever I can take that exponent and I can make it equal to whatever that remainder is. So the remainder will either be 0, 1, 2, or 3. And whatever it is, that's going to end up what I'm getting here. So 4 times 7 is 28. Subtract 3. Whoop. I get a remainder of 3. So that means that I to the 31st is the same thing as I to the 3rd. And I to the 3rd, well, that would be a negative I. All right, on this one, we're gonna have to do a little bit of division here. So 4 to the 15. We have 4 divided by 27. We have 4 divided by 71. Whoop. And we got 4 divided by 22. So 15, that would be 3 remainder 3. So I to the 15th is really I to the 3rd. 27, that would again be 6 remainder 3. So I'm going to put another I cubed here. 71, that would be 17 remainder 3. I'm going to have to rewrite that where it's actually legible. 17 remainder 3. So plus I to the 3rd. And 22 would be 5 remainder 2. So minus I squared. By plugging all these in, I get a -1 minus a -1 plus a -1. I guess I could have subtracted out those I cubes at the very beginning. Probably should have. That's all right. Minus, I'm putting i's. Those should be negative i's, negative i's, negative i's. Let me rewrite it. Those dots aren't coming out real well. Maybe I can get the eraser. There we go. Let's try that again here. So negative I minus a negative I plus a negative I minus a -1. So when I combine all my like terms here, I have a negative I plus 1. Remember that when I write the point, it's like the real number comes first. So it'd be 1 minus I. All right, so combine our like terms. Combining like terms, that was kind of the first little deal we have to deal with today. Let's try a little bit more here. What if I give you something like this here? Let's try 5 minus 7i. Plus 8 plus, whoopsies, how'd I end up over there? That's a good one. 8 plus 3i. And we'll try this one here. How about 2 minus 5i minus -1 minus 3i. And then the next batch will be -3 minus 4i minus, let's go 5 minus 9i. And I'm going to have to move myself out of the way, it looks like. Ooh, there we are. All right. Go ahead and pause the video and give it a shot. All right, we got you back here. So now, again, don't overcomplicate this, friends. We're just combining like terms. If there's a plus or minus in between, we just combine our like terms. So the -7i is going to be combined with positive 3i. 5 is combined with 8, so 5 plus I, that would be 13. negative 7i plus 3i, friends, that would be a negative 4i. All right, if there's a plus or minus in between, just do what it tells you to do. Now, what happens a lot of times is you guys see parentheses and you automatically think, oh, multiply. No, it's not multiplying. Now, rule of thumb, distribute that negative in there. So 2 plus 1 is 3. Negative 5i plus 3i is negative 2i. Distribute the negative in there. So negative 3 plus a negative 5 is negative 8. Negative 4i plus 9i would be positive 5i. Oh, friends, we are cruising. After 2 really long videos, nice, we don't have long to go here. All righty, let's keep going here though, huh? So, 7, how about I give you 3i times 5 minus 4i. And again, it's kind of nice, right? We're just a little review of what we had before. Okay, so nothing new. Just nice review of what we did back in integrated 2 and integrated 3. Apparently I don't want to write anymore. There we go. 8. Let's go 3 plus 2i and 5 minus 2i. 9. Let's try 4 plus 3i and 4 minus 3i. All right, so we are going to multiply. Notice we're just going to use our generic rectangles on these here to figure these out. I have 1 factor times 2 factors, so I'm going to, I guess I probably should have. Why don't you guys go ahead and pause? Let's try that again. Pause the video and go and solve them. All right, unpause. Or did you pause? That's the question. Tis noble. More important than to be or not to be. All right, so we have 1 factor times 2 factors. We're going to have 2 factors times 2 factors. And we have 2 factors times 2 factors. So we're going to plug everything in here. We have a 3i. We have a 5 minus 4i. So when I multiply it all the way out here, then I'm going to end up with 15i, a positive 15i, minus 12i squared. And remember, I squared is the same thing as negative 1. So that'd be negative 12 times negative 1, which is a positive 12. So what I'm left with is 12. Real number always comes first, plus 15i. All right, let's see what you guys got on this one here. We got a 3, got a positive 2i. We have a 5, minus 2i. All righty, and let's see here. Oh, we are going to end up with 15. Whoop. Oh, let's try a positive 10i. Negative 6i. And minus 4i squared. Now, if we have an I squared, we said to change that to a negative 1 again. So negative 4 times negative 1 is a positive 4. So 15 plus 4 is 19, plus 4i. Four plus 3i. 4 minus 3i. You should have seen something hopefully kind of cool with this one. And again, it shouldn't have been too terribly of a shock. Imaginary numbers, when they come in conjugates, in other words, conjugate, remember, is that term where we have one that's plus, one that's minus. Just like with radicals, if we're multiplying two numbers that have conjugates, that means that are conjugates, that means the imaginary number would go away, just like the radical went away. Imaginary numbers also go away. So -9 times -1 is a positive 9. So it turns out that's just going to be equal to 25. If they're conjugates, they go away. Pretty good so far? Because we're just about done, friends. Just about done. I'm going to write that one again. I want to refer back to it. 4 plus 3i. And we had 4 minus 3i. And we found out that that was 25. When they multiply a conjugate, they go away. So here's what I'm going to let you guys do just for the fun of it here. Let's see here. Problem number 10. Let's go with 3. Holy wow, that's a big denominator. 3 over 2 plus 5. And then we'll go 11 over, 11 will be 2 plus I, all over 2 minus I. That plus kind of looks like a 4 there. We can do better than that. And our last one, after this we'll do a little bit more with graphing, but we'll call it a day. 2 plus 4i. See, very short video today. You're like, oh, thank goodness. Yeah, the last two videos, guys, you're troopers. Those were really long because we had to cover a lot of extra stuff and have extra practice because of stuff we missed during COVID. So when we're dividing imaginary numbers, when you're dividing some imaginary number, the whole point is to just rewrite it. So that way, no matter what happens, we don't care what's in the numerator. All we want is a single real number in the denominator. Just like we need to get radicals out of the denominator, we need to get imaginary numbers out of the denominator. So this is where this idea of our conjugates are going to come back into play. Because I know that if I multiply something by a conjugate, I end up with a real number because the i's go away. So using this idea, and this is your one new idea for this section, see if you can try number 10. How would we get that imaginary number out of the denominator? And then go ahead and try to simplify. Go ahead and pause the video and try it. All right, here we go. So I see the 2 plus 5i. That means I'm going to multiply by 2 minus 5i by the bottom. But if I multiply the bottom by that, means I also have to multiply the top by that. And notice, it just turns out being one of our, on the top, we have our little regular 1 by 2, and on our bottom, we're just going to have our other rectangle. I can move that down a little bit. There we go. So we're just multiplying. That is all we're doing, friends. Division is really nothing more than a lot of multiplying. So on top, I have 3. And I'm going to multiply by 2 minus 5i. On the bottom, I have 2 plus 5i. And I have 2 minus 5i. So on top, I got 6 minus 15i. And on the bottom, I have 4 plus 10i minus 10i minus 25i squared. So negative 25 times a negative 1, which would be a positive 25. So when I combine all our like terms, I end up with on top 6 minus 15i. And on the bottom, I'm going to end up with 29. Now, if the number on the bottom can simplify into both the two top terms, then I want to simplify my fraction. But 29 is prime. Nothing will go into it besides 1 and 29, so it does not simplify. All right, friends, using that idea, see if you guys can go ahead and now go back and take a look at 11 and 12 and see if you can go ahead and figure these out. While you're doing that, I'm going to draw some things. And while you guys are finishing this up, remember, we're going to multiply by the conjugates. Multiply by the conjugates. Keep going. Well, I'm just going to be setting things up here. All right, we'll keep multiplying here. Multiplying the top and bottom by the conjugates. All right. So go ahead and pause the video if you need a little more time. All right, now I got you all back here. So on top, I got 2 plus I. I have 2 plus I. On the bottom, I have 2 plus I. I have 2 minus I. So 4 plus 2i plus 2i plus I squared. And I squared again is -1. So on top, I have 4. I lied. I have 3 plus 4i. Now we need to figure out what's on the bottom. 4 plus 2i minus 2i, there goes the imaginary numbers, just like we said they would, minus I squared. And again, I squared is a -1, so negative times a -1 is a +1. I have 5, and then the i's go away. 2 plus 4i, 3 plus 2i, we have 3 minus 2i, we have 3 plus 2i, and we're going to plug in all our numbers here. So we have 6 plus 12i, we have 4i, and we have a positive 8i squared. And again, I squared, you're probably getting tired of me saying it, I squared is -1, so that gives us a -8. So 6 minus 8, that'd be a -2, plus 16i. And then we are going to now multiply out the bottom. And again, since we're multiplying by conjugates, that means that the i's will go away. So the i's will not have it here. They will be eliminated. minus 4 I squared. So we get negative 4 times I squared, which is a positive 4. So 9 plus 4 is 13. All right, we feeling pretty good so far? I hope so. Okay, last thing. Last thing, then we'll call it a day. You guys remember what absolute value is? Absolute value. That's the distance away from 0, which we said was always a positive number. Absolute value for complex numbers, that's the distance away from the origin, or in our case, the distance away from 0 plus 0, I. And 0 plus 0, I, well, that is essentially 0. So let's go back to the one we had at the very beginning. We graphed the complex number 3 plus I. At the very beginning, we had this complex number, and we called it 3 plus I. And by the way, you'll find out second semester, a lot of times we use the letter Z to represent a complex number. So what I want to do is I want to figure out the absolute value of Z. So the absolute value of 3 plus I. So let's think about what that looked like. The absolute value of 3 plus I. This is the distance away from 0, 0. So where is 0, 0 at? It's right here. So the distance would be this value from here to here. What do you think this is going to be then? Or how we're going to do this? Do you see it yet? Kind of looks like it. If you notice, it kind of looks like our Pythagorean theorem, doesn't it? Turns out that's exactly what it is. Absolute value is nothing more than the Pythagorean theorem. So if I want to find the absolute value, so the absolute value of this complex number, I'm going to take my A value and my B value, and I'm just going to do the Pythagorean theorem. So the absolute value is going to be the Pythagorean theorem, A squared plus B squared equals C squared, or the square root of 3 squared plus 1 squared. That means the absolute value would be the square root of 10. So in other words, if I make this the absolute value Z, just in case you're wondering why I went right to that square root thing. So the hypotenuse is always equal to A squared plus B squared. And by the way, in a complex number, A plus BI? Could be a coincidence there. So we take the square root of it. We end up with the absolute value of Z equal to the square root of A squared plus B squared. Or in this case, that's why we had the square root of, we had the square root of 3 and 1, because that was A and B. So the absolute value of 3 plus I is the square root of 10. Friends, how about you try one of these yourselves, and then we will call it a day. I would like to know, what is the square root of negative 2 plus 7i? I also want you to graph the point. -2 plus 7i. All right, go ahead and pause the video and do it real quick. All right, you guys did it, I'm sure. So let me go and do it real quick. 1, 2, 3, 4, 5, 6, 7. 1, 2, maybe like that. There it is. All right, graph that point there. So this point right here is the point -2 plus 7i. What I'm asking you then is what is the distance from the origin? So if I'm just going to be doing this here, all I'm really doing here is figuring out Pythagorean theorem. So that means the absolute value is the square root of a squared, so -2 squared, plus 7 squared. So 4 plus 49. And that absolute value is the square root of 53. So the last thing we need to be able to do on complex numbers, can you find the absolute value of a complex number? All righty, friends, that's it for today. Hopefully you guys took great notes. And I will see you tomorrow morning, and we'll go over this one more time. Okay, take care.